communicated or set up communications with a host using ICMP, TCP, UDP, any protocol, subsequent communication streams tend to be quicker. The setup stream, the first packet, tends to take a longer time, but once the host is up and running and responding, communications speed up. The third, although faster than the first, was slower than the second, but still fast in the overall scheme of things. And then we get the fact that we lost no information, and it took just under 2 seconds to send 3 packets. Here's the round trip timing for the minimum, the average, as well as the maximum and deviation. So we have a deviation of just over 1 full second. Makes perfect sense. It took us 3.68 milliseconds and a fraction of a millisecond, then 1.74, and when calculated, it's roughly a 1.284 millisecond differential, not second differential, millisecond. So it was a deviation of 1.284 milliseconds as opposed to 1,000, meaning 1 full second, as 1,000 milliseconds is equal to 1 second. All 3 packets did indeed take 1,998 milliseconds, or just under 2 seconds. So again, we use ping for the purpose of communicating with remote systems. Ping supports many options, not just a packet count as we've shown you, or the ability to send 3 packets, but you could, for example, set the interval. Let's say you wanted to run a process which checks up on a host on an interval that's wider than a second, as is the default for ping. Well, using the interval option, we can change that to make it longer, for example. Let's go ahead and give that a try. And we see the I option here. We're going to set that as our next task. So ping, and let's suppose we want to send 3 packets. With the I option, let's say instead of every 1 second, every 3 seconds, the same host. This will stall or delay the pings, or spread them apart by 3 seconds as opposed to 1 second, which again is the default. Let's clear screen. And now the timing in between the first and second is 3 seconds, the second and third is 3 seconds. But the timing doesn't impact the round-trip minimum, average, and maximum deviation. The time that it takes to send 1 ICMP echo request and receive 1 ICMP echo reply is solely based on the network connectivity between the 2 hosts, not the interval that we've specified. So it still takes us a very short amount of time, generally under a full millisecond, to communicate, even if we spread out the ICMP requests. So that way we can again spread out our pings. Let's set it to 5 seconds. The first will go immediately, then 5 seconds later the second, and then 5 seconds later the third. But again, it doesn't impact the round-trip timing. The round-trip timing is a function of the network connectivity between the 2. So delays pings to 3 seconds apart, which can be useful if you are monitoring a remote system and elect not to send packets using the standard 1 second interval. So let's just note ping defaults to a standard 1 second interval. You may want to alter it. Now there are other things you can do obviously with ping, especially with Linux. For example, you can influence the byte size that you send, the packet size. The default packet size, as you saw before, is 64 bytes, but not all hosts support 64 bytes. You may need to reduce the size to, let's say, 32 bytes, and there is some overhead, an 8-byte overhead, making it 40 bytes. So if you need exactly 32 bytes, drop it by 8 to 24 with its overhead of 8 bytes, will then yield 32-byte packets. So with Linux ping, you can, or any Unix ping, you can influence the size of the packets using the S option. So again, ping is a useful diagnostic utility, but you can't always rely upon it, because, for example, we're on this system on one subnet, and if we attempted to, let's say, hit a host on the internet using ping, and the router disables ping, then ping will never get the ICMP echo reply. So you can't always rely upon it because firewalls may block it, which is why there are other protocols. For example, in addition to ping, we've got telnet. Now, we don't advocate that you use telnet for taking control of a remote system because it's a clear text, unsafe protocol. However, for diagnostic purposes, telnet is an excellent tool, and it's great for basic TCP port diagnosis. It's an excellent tool for this because if you have connectivity problems to, let's say, a TCP port that you know should be accessible, rather than using the client application that connects to the port, you can use telnet to try to connect to the port. So, connect to ports on various hosts. By connecting to those ports, you'll be able to determine whether or not the port is listening. It's equivalent to a TCP connect performed by tools such as Nmap when logged in non-privileged mode or in privileged mode, and you elect to by indicating the appropriate option to Nmap. Now let's try a simple test. We've got multiple systems on the wire listening to protocols such as 22 for SSH, 80 for web, and others. So from our system, let's test the ability to communicate with, let's say, one of the SUSE boxes on port 22 without using the SSH client. This is where telnet helps us out. Telnet, let's say 192.168.75.100 followed by the TCP port. Instead of port 23 for telnet, we'll indicate 22 for SSH. And what this will do is connect us to the port. And we will usually see a banner for the service behind the port. Let's try this. In fact, we'll try it in a new window as the non-privileged user, Linux CBT. So let's telnet, and there you see the banner, the SSH banner of the remote system. This tells us positively that the remote system is listening to SSH and will accept connection. So if someone argues or complains or makes note that they're unable to connect to a port on one of your systems, you should be able to easily tell that to that system to see whether or not it's indeed listening. And this also applies to internet-based hosts. So for example, let's use one of our public web servers. We'll telnet to www.linuxcbt.com on port 80, which is a web port, which should be listening so long as the website's up and running. Using the same shell, we'll paste the command, and there we see the remote system has picked up the phone, and if we echo the escape sequence, the default page will be dumped for the index.php page. So with that said, you can use telnet to connect to TCP ports. Connect to, and we should indicate, TCP ports on various hosts. It doesn't work with UDP, as UDP is connectionless. It doesn't support connection statuses. So you can connect to TCP ports, whatever you'd like, even SSL ports, to see if it picks up. For example, a telnet to www.linuxcbt.com on 443 will pick up the phone, as it indeed returns for SSL. That doesn't return anything to our screen because it's all encrypted, it's garbled, but nonetheless tells us that the port picks up. Now, how about connecting to a port that is not in use or is not active on one of our internal hosts, such as 2222? Telnet returns a connection refuse, and this is where you see its value as a diagnostic tool. Because if a port is listening, you should not receive connection refuse. But if it's not listening or not available for one reason or another, then you'll get connection refuse. And by one reason or another, we mean, well, you need to keep into consideration or take into consideration that there could be intermediary firewalls preventing you from connecting to the service. There may even be a firewall at the host denying access. But as a general test, you can use telnet to communicate with the port to see if it is indeed available. There's still yet many other tools. Let's move on to netstat. NetStat returns network statistics. It provides network connection information, and it does so based on the values in procnet or /procnet. So it provides network connection information. And by network we mean all protocols supported: TCP, UDP, IPv4, IPv6, and so on. Even for Unix sockets and other protocols, but we generally use it for IP as Linux is synonymous with IP. So information from procnet star. That's where it gets its information from, and it presents it to us nicely in a nice, neat format. So task, return useful information for various protocols. So for example, NetStat, with nothing, with no options, will attempt to return connection information. Let's go to our shell. And you can run this tool also as a non-privileged user, but you get more information when you run it as a privileged user. When you run it in this form, it returns everything: Unix streams or Unix sockets, datagram connections for Unix, as well as TCP, UDP. We often need to filter the information because it returns way too much information, and that's why we run its many other forms, such as netstat-a. Let's return to the shell. And if you pipe this output to less, then you get it one page full at a time. Netstat-a dumps all information, and it also resolves hosts and ports wherever possible, such as the Internet Printing Protocol, SMTP, and others. Here we see TCP connections returned first. We see the receive and send queues, the fact that the protocol is TCP, so it's sorted by TCP first, the local address, the foreign address, and the state of the port. The state of the connection in this case, which happens to reflect the state of the port. If you scroll through the list, following TCP is information for UDP, which has nothing in the state field because it's connectionless, doesn't support connection status information. However, there are services bound to UDP, such as syslog, DHCP, and others that are very important. After TCP and UDP, we then see Unix domain sockets for various programs like syslog, MySQL, various programs that make use of Unix domain sockets. So that's using netstat-a, that is, returns all protocols. But again, it's still not concise enough. It still doesn't return information in a nice, easy to manage, digestible format. Again, netstat-a returns all protocols /sockets. Now if you want to zero in on specific protocols such as TCP, which is generally where we tend to use, or the protocol that we tend to zero in on with NetStat, then use NetStat with the NTL option. This will 1. Turn off name resolution, 2. Focus on TCP, and 3. List the various listeners. So this returns all listeners. The purpose of returning all listeners is to see what ports your system is listening to. This tells you for the TCP protocol that this local system is listening to the following ports: 2208, 5801, 5900, 5901, 111, 6001, so on and so forth. Each of these protocols, of course, have distinct purposes, but indeed, our system is listening to these ports. 22 we can confirm, that's used for SSH, and the triple or quadruple colons that we see here, the triple colons that is, represents IPv6 and IPv4 connectivity. 25 is for SMTP. If we turn on the P option to NTL, it attempts to return the program that has bound to the port. So let's reset the buffer and execute P, and then for each listener, notice that the state for all of these ports is listen, not established or some other intermediary state, but listen. We see that the different programs that are responsible for the port, such as 631 for CUPS, for printing, for the Internet Printing Protocol, are returned. Now if you want to see name resolution, take off the N option. When you take off the N option, it attempts to return the names, such as TLP. This tells you the name of the host as well as the name of the protocol. We should also note that the names of the protocols come from etc services. Let's just return to the shell. In etc there is a services file which translates various ports, TCP and UDP, to names such as FTP data, FTP, SSH, Telnet, you name it. So we should just